of this week, which was called Labyrinth Curiosity. Once again, I'm trying to share my screen right now. Yeah, my computer is being laggy. Sorry. Okay. Can you see my screen?
Yeah.
I assume that's a yes. Okay, so basically, you're in an underground labyrinth, and there are n different points and n tunnels between them. So n nodes and m edges. And every time you go through a tunnel, you can go through a tunnel multiple times. You gain X points. You start off with 0, and then you're trying to go from 1 to n. And then what's the maximum point total you can achieve? This problem is a semi-standard Bellman-Ford algorithm problem. And so I'm going to explain Bellman-Ford first, and then I'll dive into how it applies to this problem. Okay, so Bellman-Ford is basically it's a algorithm that you can use in a graph with negative weight edges, and you find the optimal distance from a starting node to an end node to any other node, in fact, and then you basically have an edge list, which is a list of edges, list of the weighted edges. And so suppose in this problem, the starting edge starting node is 1 and the ending node is n. So I'll just do it to do this as the same to explain Bellman-Ford. So we start at 1, we're trying to go to n. We have, let's say, 6 total edges, 2, 3, 4, and 5. Let's just arbitrarily connect some of these. And yeah, so suppose these are the weight edges. Okay, and you have an edge list containing each of these 1, 2, 3, 4, 5, 6 different edges. So at first, everything starts at distance infinity. I'm explaining standard Bellman-Ford right now. So we're in fact trying to find the shortest path from 1 to n, not the situation in the problem. So we start off with distance 0 at 1, and then all the other distances of infinity. And then we go through all the edges, and we check if it's beneficial to use the edge in that you're currently on in the edge list. So, and you do this n times throughout the course of the Bellman-Ford algorithm. So I'll go through one step of the algorithm. And one step is basically just going through the edge list one time. So let's suppose the edge list starts here. We see if it's optimal to use this edge. It is, because this is infinity, and using this means this is at distance 1, so it's optimal. And then we check out this edge. This edge is weight. Oh, this is weight 2, and then obviously it's beneficial. So it's distance 2. We'll just check out this edge. 2 plus 3 equals 5. And this is not beneficial because obviously this is 1. 1 plus 4, that's 6. This is beneficial. 6 plus 1, 7. 7 plus 0. Oh wait. 7 plus 0 is 7. And then we do this n more times, because you know that every single shortest edge consists of n minus 1 different edges, at most n minus 1 different edges. So if you go through all the edges n minus one at least n minus one times, you'll know that you'll eventually reduce all the paths down to the shortest path. And also like I said to do this step n different times because like on the nth time, if you have a negative edge cycle, suppose like I'll just like cut this and give an example where Bellman-Ford doesn't here's the graph. So this is 1, this is 2, this is 3, this is 4. Suppose the edge weights are like -1, -1, -1, and like 1. Obviously, the like most beneficial path is weight of negative infinity because you can keep on going through these negatives. Bellman-Ford can't deal with this, but like it can detect these cycles and report them. Because on the n minus one try, like, okay, let's go to the algorithm for this. I think it'll be instructive. So on the first step, this will be 0, and then all of these will end up being -1. I think this also becomes -1, and then this one becomes 0, and then each time each of these are reduced by -1 by checking the edge list, and then like in the end, on the nth time, if you can still reduce a distance, that means that you have a negative cycle. Because normally, if you go through, if there weren't a negative cycle, and if you went through this n minus one steps, then like you're not supposed to have any more like possible reductions because it would have accounted for every single different like shortest path. So if on the nth try there is a way to reduce it, that means there is a negative cycle, and then you just print out that there is a negative cycle. And obviously, how this applies to this is that it's fairly similar, except this time instead of finding the shortest path, like trying to minimize the like weights, you're trying to maximize. And the negative cycle in this case would be like a positive cycle where you can infinitely go in a loop. And I think, yeah, if you can get infinitely large score print -1, this is like for the positive cycle case. Right, I'm just gonna jump into the implementation now. So this is just reading in the input. Can't type. Oh wait, not file reader. Using the string tokenizer to read an NNM. And then I'll define in static class called edge to store the edges logically. A and B are the nodes for the edge, and C is the distance, the weight. In this case, it's just the score. This is the constructor. And yeah, that was a fairly simple edge class. And then I'll read in the rest of the input and store them in an array list of edges. I just randomly called this variable L. I'll just copy and paste. It's kind of lazy. And make sure to do this as long, because like this is 10 to the 9, and like if you do multiple 10 to the 9s, you can get beyond the limit for an integer. I'll add the edge, and okay, I'll deal with this probably. Now we'll get to the actual part of the Bellman Ford. The limit for the number of nodes is 2,500. So I'll just create a long array of 2505, and yeah. And the score represents the like distance to each of the nodes. In this case, is the max score so far through each iteration. And then we'll go through all of these and set them equal to negative infinity. And we'll define infinity up here as, okay. As 10 to the power of 18. And we'll do negative infinity, because you want, like in the original Bellman Ford, you start out as every node has distance infinity, except this is where you're trying to minimize stuff. But when you try to maximize stuff, that means you just negate the infinities, and then it still works. So yeah. And then obviously the score of the first room, the first point starts at 0. And I'll go through the different times we do the steps. You traverse all the edges. And if it's beneficial to use that edge, and you need to make sure the distance to the first one is not negative infinity, because that means that like you haven't actually reached that node yet, and you don't want to be increasing scores when they're at negative infinity. And if it's beneficial to use that edge, then obviously just like use it. And if this is the nth iteration of the loop, that means a equals -1, and then you just print out -1. Because that means that there was a positive cycle and you can get to infinity. And then I'll create a variable here just to break out of this. Just so that if the bad tells me that if I printed out -1 already, if I didn't print out -1 already, that means I need to print out the answer. And yeah. But however, like this solution doesn't work fully. Actually, I just run this first. What is this? I'll just break this up, I guess. I don't know why this doesn't work. Okay, so let's try submitting this code. This won't actually work because there's like a special case. Yeah, test case 4. There's a special case that it doesn't account for. Let me draw out that special case. So suppose we're at node 1 here, node n here. And then like, suppose there's like a bunch of edges. There's a bunch of edges leading to n here. And then like, there's a positive cycle somewhere in the middle. But the positive cycle, if you enter that positive cycle, you can't actually like go back to n because the edges in the problem are directed. So like, so if there is a positive cycle in the middle, and like, obviously you can get infinity by going through this positive cycle, but you'll never be able to actually go to the end. So in the context of the problem, this case doesn't actually matter, and there's still an answer by just like looking at the other edges. And this is what the current solution doesn't account for. Like for right now, it just detects the positive cycle and just prints -1. But in reality, there is the answer because you can just ignore this positive cycle because it'll never, if you go into it, you'll never be able to reach node n. So you can just ignore this and look at the other edges. So that's why you have to account for that case. And like a lot of people had difficulty with that for this problem. Basically how you do this is like, you just, you invert all the edges so that instead of like them being directed towards n, you invert the edges so that they're all directed backwards. Because essentially what you're trying to do is like only consider the nodes that can actually reach node n. So in order to find all the nodes that can actually reach node n, you can just invert all the edges and do a DFS. And then like, if you can reach a node using DFS, when the edges are inverted and you start at n, that means normally when you're going forward during the normal way, you can reach node n from that node. And then you'll have a Boolean visited array and mark each one of the nodes you visit during the DFS as true if you can visit it. And then you can use that to account for the special case later. So this is our visited Boolean array. This is the inverted adjacency list. This needs to be initialized. I'll just do it at like the very beginning. And finally, we've just read DFS. I'll assume everyone knows DFS already because it's a fairly simple algorithm. Yeah. And then in the middle, we'll just call the DFS. This is a DFS from n. And when we add the edges, we need to remember to invert them. So instead of going from A to B, it'll go from B to A. And yeah. And we'll actually use the visitor right here. Because like if it forms a positive cycle, but you can't actually visit it, and it hadn't been visited in the DFS, that means it's a special case and that you can't go for the node to end. So you need to ensure that you're able to, it was visited during the DFS in order to actually print -1. And then this should be right. Okay. Does anyone have a question? Okay. I'll hand it over to number 4.